Hello, everyone. Welcome back to this week's algebraic graph theory seminar. This week, Josephine, she's going to talk about Kirchhoff-type laws for sine graphs.
Yeah, so as Tina said, I'm going to talk about Kirchhoff-type laws for sine graphs, and I'm going to start with some background information about one way that people usually think about graph theory and how we're going to slightly modify it for our approach. So first of all, graphs are often thought of as having a vertex set, an edge set, and if you want some sort of orientation, you often have a pair of maps that map the edge set into the vertex set, head and tail maps. So you can see that they take an edge and they map it to the vertex set as a head and tail. And this kind of provides a natural orientation for the edges. So we flow, from the head from the tail to the head. So we have no necessary orientation, but we can suppose that there's this imposed orientation by the two different maps. And that's useful when we create the incidence matrix of an oriented graph, because that allows a plus and a -1 entry. So we have a +1 if we say that the edge enters a vertex, and a -1 if it exits. So here you can see that edge 1 exits V1 and enters V2, and that shows up in the incidence matrix as a -1 and then a +1. So that's nice because it gives us a natural way to orient our incidence matrix. We also have the adjacency matrix of the graph, and this doesn't depend at all on the orientation of our map. And we just have each entry is the sum of the adjacencies between vertices V and W. So here there's no multi-edges, so all of our values are either 1 or 0. And then we can define a Laplacian, and a Laplacian can be defined two different ways, depending on your preference, but they actually come out to the same Laplacian. So we have degree minus adjacency, or our incidence matrix times our transpose for this oriented incidence matrix. The degree matrix is just a diagonal matrix where the degree of each vertex is down the diagonal. So here's a little Laplacian we obtained for this specific graph that we've been using as an example, where we have the degrees 3, 2, 3, and 2 again. You can see that down the diagonal. And this is also obtained by taking that incidence matrix from a couple slides ago and multiplying it by its transpose. One thing that's really nice is you might wonder, well, our incidence matrix had an orientation on it. And what's nice is that the Laplacian is going to be the same regardless of the orientation you chose. So every orientation will provide us with the same Laplacian. And another way we like to think about degrees regarding the incidence matrix is it's the number of incidences that appear at a certain vertex. So how does this relate to sine graphs? So the Laplacian of a sine graph is going to be degree minus adjacency still. And what happens here is an adjacency is now just signed. So you can see that this is the same graph, but we've made two of our edges negative. And I've represented this as a bidirected graph. That's an easy way to look between orientations and sine graphs. And we have these four ones that are now showing up as positive, whereas they were negative in our previous Laplacian. And that's because we're subtracting a negative adjacency, which flips the sign back to positive when it shows up in our Laplacian. So positive adjacencies appear as negatives, and negative adjacencies will appear as positives in the Laplacian just because of this subtraction. So I want to modify this definition slightly. And instead of looking at graphs, we're going to look at incidence hypergraphs. So that's going to be a vertex set, an edge set, an incidence set, and then two maps that take the incidences to the vertices and the incidences to the edges. The way this will work is instead of having vertex, edge, vertex, we'll have vertex, incidence, edge, incidence, vertex. So an edge will be incident to a vertex if their pre-images intersect. So if the set of their pre-images under the appropriate maps has an intersecting incidence in it. And this is an easy way to have multi-edges. So we have these four vertices here, W1 through W4, the single edge F1, and each vertex is incident to this edge F1 because there's an incidence, these J1s through J4 that map to it. And this allows us to travel locally among our hyperedges. So you can imagine if we started at W1, I could use J1 to get to edge F1. And then if I wanted, I could pick any other incidence, so maybe J3, and then I would get to W3. So that would be an adjacency between W1 and W3 as I travel locally through F1. And I can also orient my incidences. This is going to allow me to get back to sine graphs. So I have an incidence orientation function where I just send the incidences to plus or -1. And we're going to think of this the same way we did as orientations earlier, where it'll be -1 if it exits a vertex and +1 if it enters. And then a bidirected graph can be simply thought of as an oriented hypergraph where each edge contains exactly two incidences. So the theories will still work because we're just going to restrict if we want to look at it that way. And so we can actually do the incidence matrix the same way, basically, where we have the VE entry to be the sum of the incidence orientations between a vertex and an edge. So here's a hypergraph. We have two edges and one 3 edge. We even allow multiple incidences to appear at a single vertex. So vertex 3 is incident to edge 3 twice, which is how this 2 is going to show up in this incidence matrix. This allows us to define an extra figure. So adjacencies and loops are probably familiar to most people because we have an adjacency to be an incidence monic map of a path into a graph. And a loop is not a vertex monic one, but a backstep can now be defined because a backstep is a non-incidence monic map of the path of length 1 into the graph. So here I have this single edge that has 4 vertices and 5 incidences. So these incidences are just the lines. And here you can see in color all of the various backsteps I could take in the graph. And that's start at a vertex, use an incidence to get to the edge, and then turn around and return to your vertex along the same incidence that you already used. And now I want to talk about what the sign of an adjacency is. So the sign of an adjacency is just the negative product of the signs of its incidences. So we have 2 ways you can have a positive adjacency, if the arrows flow in either direction. And you have 2 ways you can have a negative adjacency if your 2 arrows along your adjacency fight in either direction. So this just has to do with whether your incidence signs agree with each other or disagree. So you can think about here as a hyperedge, and I've highlighted in red all of the negative local adjacencies and in blue all of the positive local adjacencies. So you could just imagine that if I wanted to travel from this top left vertex down to this bottom right vertex, my 2 arrows fight along my incidences, so that's a negative adjacency that I would be using. Or if I went from the top left to the top right, the arrows agree, and so I'm exiting and then entering, so that's a positive adjacency. And that's kind of the natural instinct. If the arrows agree, you want it to be positive, and if they fight, you want it to be negative. And this definition of signing extends nicely to backsteps. Since in a backstep, you're going to reuse the same incidence twice. It will be, you could think of it as sigma I squared and then negated, so it's always going to be a negative adjacency. So the Laplacian matrix of an oriented hypergraph is still degree minus adjacency, but with this incidence matrix where you have the sum of the incidences in each place, it is now also a transpose. So we again are preserving that definition. So here's an example that has the 3 edge and then the 2 edges. And here is its Laplacian matrix. You can see that the degree still works out just fine. One thing to note is vertex 3 has degree 2 because it has 2 incidences at it, even though those incidences are both to the same edge. So it is important that we calculate degree as the number of incidences at a vertex, not the number of edges that are adjacent or incident to a vertex. And this is nice because it has a weak walk theorem as well associated with it. The VW entry of the negative Laplacian is the number of positive paths of length 1 from V to W minus the number of negative paths of length 1 from V to W. So the entries are actually counting adjacencies, loops, and backsteps, which is just a nice fun fact. So I've been talking a little bit about figures in a graph. So many people are, I'm sure everyone here is familiar with the spanning tree. So it's a connected acyclic spanning subgraph. There's a little 4 vertex graph and it's 8 spanning trees. And the reason we care about this is we're going to talk about a lot about figures in a graph, and spanning trees are probably the most familiar. So the next thing I want to introduce, which I need for the Kirchhoff's laws, are K arborescences. So a K arborescence is a set of K disjointed rooted trees that span a graph. So here, for a more interesting example, is a slightly bigger graph than the previous example. And here I have some of its 2 arborescences. So all of these have a root at V5 and a root at V4. And you can see that there's 2 trees and they span all the vertices of the graph. So a K arborescence would have K trees, but these are just some 2 arborescences for the specific graph. And then Sachs defined some various other figures in a graph. So an elementary figure is a cycle on n vertices, where n is at least 2, a path of length 1, or an isolated vertex. And then from these, he defines something called basic figures, which are a disjoint union of elementary figures. And he has a script UK to be the set of all basic figures with exactly K isolated vertices. So this would be in U2, so I have 2 isolated vertices and 1 path. Each of these components individually is an elementary figure. This would be in U1, I have a single isolated vertex and a cycle. And then this last figure here would be in U0, it's a cycle on 4 vertices, and so it's actually a basic figure and an elementary figure because it only contains 1 component. And these are nice because Sachs's theorem is a sum over all of them. So he says that you can calculate the characteristic polynomial of the adjacency matrix for a graph by summing over these figures with the appropriate signing function where you look at the number of components and the number of cycles in a component. And then when you take the determinant, you're summing over these, and you get the characteristic polynomial. So you could look at the coefficients and say, if you look at this -5 in front of x squared, it means that there are 5 figures that are made up of 2 isolated vertices. That's what the x squared component tells us. And then the remaining parts of it form the rest of the basic figure. So if you isolate these top 2 vertices, for example, then there's a path between the other 2 vertices of length 1. And you can do that for any pair that you isolate, with the exception of V2 and V4, which can't be isolated. There's a path between the other 2 of length 1, and there's 5 ways to do that because there's 5 edges. So these coefficients are actually just counting the number of basic figures with the appropriate number of isolated vertices. And we care about this because we're going to extend this idea using our hypergraph idea. So we're going to define something called a contributor, and this is sort of the extension of this basic figure idea. And it's going to be an incidence preserving map of a disjoint unions of paths of length 1 into a graph, such that the tail set covers the vertex set, and so does the head set. So it's kind of like a flag planting game. You can imagine you take your graph, and at each vertex you plant a flag. I've done them here in different colors. And then I'm going to basically allow all of these to fall so that I cover the vertex set again. So here are some ways that this could happen. For example, I could have all of them fall in to create this 4 cycle. That's represented by the permutation 1, 2, 3, 4. I could have 3 of them fall to 1, 2, and 3, and that forces this 4th one down here to fold back on itself as a back step. And there's 2 different ways that could happen. So this permutation is counted twice. And then there's a couple different things we call identity permutations. Anytime everything falls as a back step, that's an identity permutation. And you can see that it could fall in this sort of circular way as a back steps, which is related to the figure above it, which we'll talk a bit more about later. Or it could fall with this yellow one falling down the diagonal, and possibly this green one falling toward the yellow one, and that's related to the figure above as well. We also allow things to fall as digons. So we could have these 2 pairs of multi-edges where we form these 2 digons here, where 1 goes to 2, 2 goes back to 1, 3 goes to 4, and 4 goes back to 2, or 4 goes back to 3. So we're creating these sets of figures. And this is nice because it now allows us to kind of up with a similar theorem where we're counting these figures. So for an oriented hypergraph with a Laplacian matrix, the sum, the characteristic polynomial for the Laplacian, and there's a version of this for the adjacency matrix as well with a slightly different signing function, the sum over all these figures with appropriate signs, and then we take each figure and we look at -1 to the number of even circles, back steps, and negative components in it. And I know there's a lot of notation here, but what we're basically doing is we're looking at all possible sets where we force the U set to go to the W set, and looking at all ways to finish those contributors. This L0 is called the loading, and what it does is it temporarily adds all missing incidences so that all figures exist, but we sign them 0 so that we only actually sum over the figures that do exist. But having everything temporarily exist makes the math a lot easier. So I'm going to do an example of what's happening here. So if I take the determinant of a Laplacian, and this Laplacian is for a graph, which I'll show in a minute, which is just a triangle, basically. You can calculate out this Laplacian, but we are putting an X in every entry signed with the location of the entry. And you get this, really long polynomial. But each of these terms is going to have meaning. So I've highlighted a couple. We have x11, x22, x33. And we also have the 1, 1, 2, 2, 1, which has a negative coefficient. And then we have the 2, 3, 3, 1, which also has a negative coefficient. And so what's happening here is this single edge with 3 vertices. This is what the Laplacian is for. And when you take this term here, it's counting the number of ways you can have a contributor where I took everything and had a back step. It's saying 1 goes to 1, 2 goes to 2, and 3 goes to 3, and then I removed them. So that's 3 isolated vertices as a figure. This one here is saying send 1 to itself, 2 to itself, and you can do whatever you want with 3. In this particular example, the only way to finish this figure is to send 3 to itself as well. And then you remove these 2, so this is the final figure you'd be left with. And there's only one way to do that because there's a single back step. Is if you remember, back steps are always negative. That's why there was the negative sign in front of this term. Here you have, I specified I wanted to send vertex 2 to vertex 3, vertex 3 to vertex 1. And the only way to finish this particular contributor is to then send 3 to 1, do this triangle. But then I remove the 2 edges that I've specified because I'm choosing the X instead of the adjacency. And I get this final figure, which is also signed negative because of the original circle. So each of these terms is actually counting all of the figures of a specific type. And you can get Sachs's theorem back from this by appropriately, for the adjacency matrix version, appropriately setting all x's to x if they are on the diagonal, and all the other x's off the diagonal to 0. You can reclaim Zach's theorem from this. And another nice fact is if you actually just want the value of the determinant of the Laplacian for a hypergraph, it is the sum over all the contributors, -1 to the number of positive circles in the contributor. And when I say circles here, I do mean cycles. We're using the word circle because we have all these permutations for each contributor, and since in a permutation you have cycles, it gets very confusing to use cycles for both cycles in the graph and cycles in the permutation. So we're calling cycles in a graph circles just for clarency's sake. So yeah, you can get Zach's theorem by restricting to graphs and then using only backstep-free ones. And it does work for the permanent. You just have a slightly different signing function if you want the permanent instead of the determinant. And a really fun fact is the permanent of the signless Laplacian actually counts the total number of contributors. So if you want a contributor count for a graph, that's a pretty easy calculation to do. Then there's also the matrix tree theorem, which is related to this as well. So if you take the Lij minor of a graph, the Laplacian of a graph, and you take the appropriate sign and then determine if that minor, you get the tree number of a graph. So here we have that example I was looking at earlier, and it's Laplacian. And if I took, say, the 1, 1 minor of this, you can imagine crossing out the first row and column, and I took that determinant, I would get 8, which is the total number of trees for this graph. And the fun thing is that this can be reclaimed as a corollary of the total minor polynomial, which I'll talk about a little later when it shows up in another proof. So how is this all related to Kirchhoff's laws? Well, it's related through this arborescences. And so first I'm going to define this interesting bracket notation. And this bracket notation is if you have 4 vertices in a graph, we define this bracket U1, W1, U2, W2 to be the number of 2 arborescences with one component rooted at U1 containing W1 and the other rooted at U2 containing W2. So here we have that graph on 6 vertices again. And here you might remember these figures. These are 2 arborescences of the form V5, V6, V4, V1. So each of them has one component of the 2 arborescence rooted at V5. You can see it here, containing V6, and that's this single path of length 1. And the other component is rooted at V4 and contains vertex 1 as well. And it doesn't have to contain it as an adjacency, as you can see in this bottom left figure, it just has to contain it somewhere in the tree. So these are all these arborescences of this form. So why do we care about this bracket notation? Well, for Kirchhoff's laws, with a graph with source U1 and sink U2 and 2 other vertices, the W1, W2 transpedance, which is what the Kirchhoff's laws are counting, is actually defined to be the difference between these 2 bracket notations where we swap the order of the W's. So it's U1, W1, comma U2, W2 minus U1, W2, comma U2, W1. So what this is really saying is that this transpedance value is the number of 2 arborescences with the component U1 containing W1, U2 containing W2, minus the number of 2 arborescences where we have component U1 containing W2 and U2 containing W1. So the transpedance value for V5, V4, that's remember source V5, sink V4, V6, V1, is going to be these 4 figures here, and it's -0. And the reason this one is -0 is because if I wanted to have a transpedance, so a 2 arborescence, where I had a root at V5 and I wanted to contain V1, I'm either going to need to go through vertex 6 or vertex 4. There's no other way for me to get from 5 to 1. But if I do that, there's no way for me to have a disjoint second tree that contains vertex 4 and vertex 6. So there are no 2 arborescences of this second bracket form. So that makes this calculation nice and easy and makes it 4. Now, Brooks, Smithstone, and Tutte said that the transpedance is related to the Laplacian as follows. You can actually just calculate it by taking the determinant of the U1, U2, W1, W2 minor with the second ordered cofactor sign. So what that means is you take the U1, W1 minor and its cofactor sign, and then within that minor, you take the U2, W2 minor and its cofactor sign relative to the previous minor. And that will give you this transpedance value. And that's why we care so much about these polynomials and Laplacians, is because we're going to use them to calculate our transpedances from Kirchhoff's laws. So what do Kirchhoff's laws actually say? They say that if you have a graph with source U1, I'm missing a word there, and sink U2, that the following 4 facts hold. You have the degeneracy condition, which is if U1 with the U's or the W's repeat itself, the transpedance value is 0. if you take the U's or the W's and you swap their order, you negate the flow of energy. So energy reversal. This is generally written as a sum around a cycle of length 3, but this clearly extends to a cycle of any length, and that's if you sum around a cycle. So the W's go 1 to 2, 2 to 3, and then 3 back to 1. But the U's remain the same. You have the same source and sink throughout. It sums to 0, so you have cycle conservation of energy. And then the last one is the most confusingly written, but it's basically saying if you look at all vertices adjacent to a specific vertex W1, and you look at the appropriate you look at the transpedance value with the appropriate indicator if it is present in the adjacency matrix, or Laplacian matrix actually, and then you look at these transpedance sums, what you get is that it is the tree number times the Kronecker delta function minus the tree number times this other Kronecker delta function. And so what this is actually saying, because it's a little bit confusing, is that if you sum all of the transpedance values entering a vertex and exiting a vertex, you get 0. Unless that vertex is the source or the sink. And that's what this Kronecker delta is telling you. If your vertex is the source, which is this Kronecker delta U1, W1, that tells you your tree number is going to be negative the tree number. So this the source vertex puts the tree number value into the graph, and then the sink vertex has the tree number value enter it. So what does this look like as an example? So here I've labeled all the transpedance values around this graph, and I've fixed the source and the sink. So I fixed the source to be V5 and the sink to be V4. And then you can see that my second two numbers tell you which edge I'm looking at. So this is the 5,4 edge. What is its transpedance value? This is the 5,6 edge. What is its transpedance value? And so on. And you can just calculate these, as said in a previous theorem, from the determinant of the Laplacian. But let's look at how these actually apply to the laws. The first one I want to talk about is the sum around a circle along along the natural source sink orientation being 0. So if I started, say, at V1, I'm traveling toward the source along this edge, or the sink along this edge. So it's a natural orientation, so it's positive. So it's 1, and then 1, and then 1. So that sums to 3. And then I'm traveling away from the sink. That negates this transpedance value. That's -3. And +3 plus -3 is 0. So the sum around a circle is 0 using the natural source sink orientation. And if you look at the net sum at a source or a sink, vertex 5 has 11 going out and 4 going out, so 15 going out total. And if you look at vertex for the sink, you can see it has 11, 3, and 1, which is also 15 coming in. And the tree number of this graph is indeed 15. So there are 15 spanning trees. So that shows that the net sum and at any source or sink is 15. And then if we want to check another vertex, say maybe V1, I have 4 entering, and then I have 4 exiting, 1 here and 3 here. So then sum at any non-source sink vertex is indeed 0. So we're going to use these contributors from earlier to extend this to work for sine graphs. And the first thing we need to do is to find a little bit more information about those figures. So we say that two contributors are tail equivalent if they have identical tail incidence maps. And I'll show you what that means in this image in a moment. But I also want to say that the activation order of a tail equivalence class says that contributor C is less than contributor C prime if there exists a sequence of backsteps unpacking that turns C into C prime. And these definitions are a little bit more natural than they might sound. So here I have 2 different sets of tail equivalent contributors. And you can see that where that initial backstep falls, when I started a vertex and I enter an edge, I basically picked to enter the same edge in both of the contributors in the pair. So that's what I mean by they have tail equivalents, identical tail incidence maps. I'm choosing the same initial incidence for the tail. What happens with the head after that doesn't matter, but they have the same initial tail start. And what I mean by backstep unpacking is I also have that these two have the bottom contributor being less in the activation order than the top contributor. What you can do is you can imagine taking this backstep and folding it out the direction it wants to go. This one wants to fold out to this top vertex, and it wants to fold out along the side and so on. And if you were to fold it all out, you would get the contributor above it. It's not always the case that every backstep unfolds. If you look at this other pair, I can't fold out this green backstep because the other 3 will fold out to form a cycle. So it gets stuck where it is. But these are also going to be less than each other. This one is also going to be less than the one above it in the unpacking order. That's what I mean by tail equivalence and activation order. And we need some other information too. So for a bidirected graph, all the activation subclasses are actually Boolean lattices. And that's going to be a really handy fact when we're looking at the Kirchhoff's laws. And the class is going to sum to 0 if any contributor in the class contains a positive circle. Finally, we have the reduced activation classes are the set of contributors where we send the U to W and then we remove them. And if you remember in previous examples, when we were looking at that sum for the determinant over contributors, I said we had this UW set that we were going to remove, and we just denoted by this A hat. And we have the script A hat should be the set of all reduced activation classes. So that's the set of all of these A hats with specific U's and W's chosen. So for a bidirected graph, like I said, that activation subclasses are all Boolean lattices, and a class sums to 0 if it contains a positive circle. So what does that look like? So here are just some of the activation classes where I send v5 to v4. So I've shown the full activation class, and then I grayed out the contributors in each one where 5 doesn't go to 4. And you're left with these sublattices, and you can see that each one is actually a Boolean lattice. They're pretty small, so it's easy to check that. These edges show what is less than something else in the order, and we have the lowest thing on the bottom because the lowest thing is the identity for each activation class. So these are all Boolean lattices. And why is that so useful? Well, we know that for a bidirected graph, the set of all elements in single element reduced activation classes is unpacking equivalent to k arborescences, where k is the length of this U set that we're removing. And that is starting to get us back to the transpedances, since those are counting two arborescences. So that's getting closer to relating these contributors to the Kirchhoff's laws. So here I have one specific class where we had two elements. You can see that they're related by this edge, so it's a Boolean lattice. And I'm looking at a v5 goes to v4 class, and then I'm going to take a subclass where I also have v2 goes to v3. So of these two contributors where v5 goes to 4, only the top one has v2 go to v3, and I'm going to remove it. And that leaves me with this final figure where I've removed 5 goes to 4 and 2 goes to 3. And this is a single form. I don't have any backsteps to unpack, but I would if I had any backsteps to unpack, I would. And what I'm left with is a 2 arborescence of the graph. If I pick k to be 1 here, this is how you can get the matrix tree theorem from the contributors. So I've now figured out how to take all of my contributors and use these activation classes to count these 2 arborescences. So why is this useful? Well, there's actually a bijection between the Tutte 2 arborescences of this particular bracket form and the single element reduced activation classes where I send U1 to W1. So here are some activation classes where I'm sending v5 to v4 and v1 to v6. Here are 4 of them that are a single element class, and then 1 that is a 2 element class. If you look at these single element classes and you imagine folding out the back steps, you would see that each one of them is a 2 arborescence, where I have the v5 goes to v4, and I have the v5 is in a tree with v1, and v4 is in a tree with v6, and that they are disjoint, which is that property that we wanted earlier when we were counting 2 arborescences for Tutte. Here in this activation class that does not have 1 element, it has 2, and it's a Boolean lattice. When I look at folding things out, I actually get this 2 cycle here, and so it's not an arborescence of the form that we want. So that's why we only have this bijection into the single element reduced activation classes. The nice thing too is that positive circles cause cancellation. So these non-trivial subclasses are always going to cancel if you have a graph. They won't always cancel in a sine graph, but for graphs, they always cancel. And that makes the math very nice for graphs. So we're going to define a new transpedance value. We're going to define this transpedance value based on the determinant using that characteristic polynomial that we've modified, so that total minor polynomial where we added all of the extra x's. We had that interesting signing function based on contributors. So we're going to calculate this transpedance value to be the sum over the contributors with this specific U and W set, the non-zero ones in that loading, and we're going to just take the signing function straight from our total minor polynomial. So we're doing it very similar to how Tutte had the theorem, or Tutte, Brookstone, and Smith had the theorem where they could calculate their transpedance value from the specific minor of the Laplacian. We are basically doing that exact same thing, but we're now using the value that is obtained by counting over the contributors instead of just taking the specific minor in the Laplacian. And this is the degree 2 monomial coefficient for the total minor polynomial. So that total minor polynomial actually has in it the coefficients for all the arborescence counts. So I just put that theorem again so we could see it right here. But the reason this is so handy is if G is a graph instead of a Sine graph or an oriented hypergraph, then Tutte's transpedance number is the same as this contributor-transpedance with a possible sign adjustment depending on the number of vertices. So if the number of vertices is even, these two values are exactly the same for graphs. And if the number of vertices are odd, then you just negate all of Tutte's values and you'll get these contributor-transpedance values. And if all edges in a graph are positive, then all the non-trivial subclasses cancel over all source sync pairs, and you're just going to be able to exactly reclaim the Tutte, Brookstone, and Smith results. But how do these work for sine graphs? So if you have a sine graph with a source U1 and sink U2 and two other vertices, then the first two results of the Kirchhoff-type laws immediately hold. So you immediately get that the contributor-transpedance value, whoops, I went back a slide. You immediately get the degeneracy hold. So if I repeat the U's or the W's, I send a 0. And if I swap the W's or the U's, I also send a 0. And so the proofs of these are actually pretty straightforward. So for the first one, U1 is not allowed to go to both W1 and W2 and be a contributor. That's just by the definition, because you're mapping paths of length 1 in, and a path can't go to two different places if it's of length 1. So for the proof of 2, that one's a little more involved, but the basic idea of it is that if you change the order of the U's or the W's, you're adding or removing exactly one even cycle in the graph. And if you remember the signing function, it was -1 to the number of cycles, negative components, and backsteps. So if the only thing I'm doing is changing the number of even circles by exactly 1, I'm definitely going to be changing the sign. In order to look at the second two parts of Kirchhoff's laws, we need to define a couple other things. So we're going to have this M minus UW be the set of maximal elements that are positive circle free. So in each activation class, you have this maximal element because it's a Boolean lattice. So we're just picking the set to be the set of the maximal elements that do not contain any positive circles. And since this is a sine graph, we do have signs on our circles. And we have a theorem that states that if your graph is signed, then this transpedance sum is actually just the sum over all of these maximal elements to the signing function times the number of negative circles in that maximal contributor. So that makes it even easier to calculate because now we don't have to sum over all contributors of the type. The only non-arborescence contributors that are going to appear have all negative circles within their activation class. And we're going to see why this holds. So the reason this holds is a little bit complicated, but the general gist of the proof is that if you have a sine graph with a source and sink, I'm just going to use this shorthand notation for the set of all reduced activation classes and a single reduced activation class. I have that this, just from the definition, the sum of over all the reduced activation classes and all the contributors in them and the sign of the contributor is this the contributor-transpedance value. And I could break this sum up into two sets of activation classes, the ones where they are negative and the ones where they are not negative, so positive. So I'm breaking up the sum, and it doesn't matter that I'm breaking up this sum because I'm just splitting the activation classes into two categories, but I'm still summing over all of them. And again, each of them form Boolean lattices, and that way I can calculate each sum separately since I know there's going to be no overlap between the two. So I have a couple cases I have to look at. If I have two contributors in the same sum that differ by a negative circle of the length L, what happens? There we go. If this length is odd, then when I take a contributor, remember C prime is slightly higher than C in the activation order. I take the contributor and I'm going to have one negative component that gets removed and a negative circle of length L. And I can pull out this L minus 1 just as a coefficient. And since L is odd, this is even, so it goes away. And this by definition is the sign of this contributor here. This contributor sign is the same if they differ by a negative circle of length L. And if the circle is even, then when I pull it out, I'm changing the number of even cycles as well. So this is L minus 2, and since L is even this time, the contributor sign is still the same. So if I have two contributors in an activation class that differ by a negative circle, they have the same sign. So that's good for my first sum. So now I need to consider my second one. What happens, or okay, I forgot this line. And the number of such signs is just the number of negative circles that I can pull out. This 2 to the nm is counting the total number of contributors in the Boolean lattice, and they all have the same sign we've just shown. Now, if they differ by a positive circle, they're going to fall into my second category of the two sums that I broke up. And if I look at my first case, if this length is odd, when I pull it out, because it's a positive circle, I'm not changing my number of negative circles. I'm just having the number of backsteps is going to change. I get -1 to the L. L is odd, so that flips the sign. If it's even, I'm going to be changing the number of even circles and the number of backsteps. So I'll get L minus 1 when I pull these out. And so again, the sign will change because L is even. So if my circle is even, or is positive, I change the sign, and if it's negative, I don't. So what's happening here is the second sum is going to completely collapse in on itself, because as you move up and down this Boolean lattice, you alternate signs. The second sum goes to 0, and the first sum is just the sign of the maximal contributor and the number of things in each Boolean lattice, which is 2 to the nm. And that shows that that result holds. So why do we need this? Well, we need this to define our version of cycle conservation and vertex conservation, which aren't exactly conservation anymore in a Sine graph. So I'm going to have the C1 hat not equal to 0 of G and the U set and the W set be the single element reduced activation classes. Now, what this cycle conservation now is, and it's again shown here for three vertices, but it does extend to any number of vertices in a cycle, is that there's actually a matching between the elements of each of these sets. And so what the difference in the sets here is this W portion. So as you go around the cycle, I can match elements of I can match contributors to other contributors. So there's a matching, but there is not necessarily cancellation among their sign. So I know that the non-trivial classes cancel, there's a positive circle. So what this means is the best I can actually do in a Sine graph is pair off sequential elements of the reduced contributors, but I'd still have to determine their sign to actually calculate my transpedance values. So cycle conservation in a graph is a consequence of the cancellation of non-trivial classes and the fact that elements have this alternating sign, matching sign property. And this just doesn't happen in a Sine graph anymore. So what does this kind of look like? This is going to be a sketch of the proof again, because it's kind of a long actual proof. But the idea is that if you have a source and a sink, and then 3 other vertices, and the general case again extends to cycles of longer size, you can take a contributor in this first set of contributors. And because we're using the loading, all these edges exist if we need them to. They're signed 0, but they technically exist temporarily. And since they're in the set that we're going to be removing at the end, it's fine to use them. What we want to do is take this contributor and translate it from the first set to a contributor in the second set to show that I can match it to another contributor, and then show that there is no equivalent contributor in my third set. So the idea is that this vertex W3 has to be linked to this path between U1 and W1, or to the path between W2 and U2. Without loss of generality for this specific image, we're going to suppose it's linked to the path between U1 and W1. And how do we know that these two paths exist? Well, the definition of contributor is telling us that we have U1 in a component with W1 and U2 in a component with W2. And these are connected components. So if I have a connected component containing U1 and W1, there is a path between them. Similarly, if there's a connected component containing U2 and W2, there is a path between them. So I'm assuming that this is linked to this path somehow, and I'm going to send it to this vertex W prime. It's connected somehow. And now I'm going to form this path P prime just by taking whatever path I need to do to get to there. And I need to know, and I want to note that this P prime cannot contain this edge W1, W2, because W1 and W2 are in different components by the definition of contributor. And now I can introduce this edge W3 to W2 because I'm in the loading, so I can add edges if I need them. And this forms a unique U1 to W2 path. And I know it's unique because previously these were two separate components, and I've added a single edge to make these two components connected. So I have to use that edge when I'm traveling from one component to the other. And I'm calling this long path, this path here, P double prime. So that's P prime union this particular edge, union the path from W2 to U2 in that second component. And it's important to note that this is going to use exactly one of EW1, EW23, and EW31. Because I'm adding whichever edge I happen to be missing, which in this specific case that I've shown here is the W2, W3 edge. But I know I'm not going to be using the other two edges because of the definition of contributor has assured me that those other edges don't exist in my picture. And then I remove this edge, and I'm going to reverse this U1 to W prime part of this path, and then pack all of my adjacencies, and pack means basically fold them back into back steps away from this path. And this is a little confusing, but what this basically does is reverses the unpacking process that I've done and leaves me with a unique contributor in this set here with the edge that I've added in being the one that gets removed. And I know that there's no corresponding contributor in my final set because if I had a path that contained E3W1, then it has to use exactly one of these three edges. And since I know that in this particular contributor, I've chosen to use W3, W2, I know I can't be using W3, W1. So just the definition of contributor allows us to show that there's a matching between a contributor in another set, and that contributor does not have something to match to in any other set in our cycle. And that's the general idea of this proof. So that's how you would show cycle conservation. Now, vertex conservation, again, is a little trickier in Sine Graphs because you don't have this really nice cancellation in the Boolean lattices anymore. We let G be a Sine Graph with a source and a sink, and we pick V to be any other vertex. We break this up into two cases. If the vertex is not the source of the sink, then all we can say is there's a matching between the contributors that enter the vertex and exit. So the number of contributors that enter the vertex and the number of contributors that exit the vertex, as they're counted by the sum, are the same. And if you are the source of the sink, then the number of contributors that exit the source are the same as the number that enter the sink. So it's a very similar idea to the Brooks, Smithstone, and Tutte Transpedance laws, but we have a slight fact of we can only say something about the set sizes, not cancellation. So I'm going to show an example to kind of show what this is actually doing. So we're going to use a graph, this graph here. I've marked all the adjacencies as positive or negative. And I'm going to have source V5 and sink V4, and we're going to look at this transpedance value V5, V4, V5, V4. So that means we're going to have a back step at V5, send V5 to V5, and V4 to V4, and then we're going to remove them. So here is the set of all the non-cancellative figures. So you can see the two isolated vertices at the bottom are where I have the back steps that got removed. And you can see that I do have these trivial activation classes. I have these two classes here that are Boolean lattices that contain more than one element. And they do not cancel because I have negative circles. In a graph, these two would cancel. So these 12 figures represent the 12 non-cancellative contributors contributing to the sum. And if you took the appropriate determinant value, you would get plus or minus 12 for this edge, depending on the direction of travel. If you were in a graph, and every edge were positive, so these three edges would also be positive, these two Boolean lattices at the end would cancel, and so the transpedance value in this graph, if all edges were positive, would be 8, because these only figures that remain would be these original 8. So that's a pretty clear example of how you get different values if you look at a sine graph versus a graph, because I'm no longer having this nice cancellation here. So one thing to note, though, is there's actually many more cancellative classes. So here's a set of a bunch of Boolean classes that cancel for the previous example. And the reason these are all going to cancel is they use an adjacency twice in the contributor figure, and that is always going to be a positive circle. And remember, we said if there's a positive circle, the whole class is going to cancel. But these are nice because they do give a hypothetical maximum for each edge, and they're counted by the permanent. So if you want to know the total number, you just use the permanent instead of the determinant when you're doing your calculations. Another important note is that these transpedances are labeling adjacencies, not edges. And so one open problem, I guess, as an extent of this is, what would be the hypergraphic analog of this? Because in hypergraphs, we have local adjacencies. And since these transpedances are labeling local adjacencies as opposed to just the edges, there should be a way to extend the theory. So one final fun result is that a contributor is counted on an edge if and only if it contains a unique source sink path in the graph union in that edge that avoids negative circles. So I'm just going to talk about what this means by these unique source sink path. So here's this graph again, and I've labeled the transpedance values. And then the next one, I've shown what the contributors that are being counted by these transpedance values actually are. And so you can imagine that you add in the edge that you're on to the figure. So if you look at this very top one here, if I added in the missing edge, then that forms a unique path from my source to my sink inside that contributor. And that works for every contributor here. You add in the missing edge and you'll get a unique source sink path. So over here on the right, I've shown that if I look at this particular source sink path, here are the set of all contributors that contain it. And you can see that they appear along the edges of that source sink path in the count. And so if you look at a graph, this is really cool because you can show from this that Tutte's transpedances are actually counting spanning trees in a sort based on the shortest source sink path in the spanning tree. The spanning tree gets placed in the count for the edge where it contains its shortest source sink path if that edge is added. That's all. Thank you.